The main way that adversarial machine learning is relevant to the generative modeling problem is through the generative adversarial networks framework that I developed with my collaborators at University of Montreal in 2014. The basic idea behind this framework is we make a contrived game between two different players. I say it's contrived because we actually control both players and we want them to compete. You'll see later there are a lot of situations in adversarial machine learning where we don't get to opt in. There really is someone attacking a service we're trying to build. But here for the generative adversarial networks framework, we create an imaginary conflict in order to force both players to get better. One of the players is a network called the discriminator that we represent with a capital letter D. The idea of the discriminator is that it's a deep neural network that acts as a classifier. It looks at the input and it guesses whether the input is real or fake. So for example, we might load this real photo of a moth shown on the left side of the slide and run it through the discriminator network. The discriminator network will then try to output a number near 1, indicating that the probability of the input being real rather than fake is high. We start to see that this is a game when we bring in the other player, the generator. The generator takes random noise and transforms it to produce outputs that resemble the training data. Early in training, the generator will not actually produce realistic images. I've illustrated this by showing the image of the animal that is kind of like a cow that is both quadrupedal and bipedal at the same time. This is a defective sample that came from a generator network. And over the course of learning, we will train the discriminator to reject these kinds of images. The way it works is we begin by sampling a noise vector that we call Z. You can think of noise as being a little bit like the seed for a pseudo-random number generator. It's a source of randomness that allows an otherwise deterministic system to have many different behaviors. We then take that noise vector Z and we transform it until we get something in the same format as the training data, using a neural network called the generator, represented by capital letter G. After we've obtained this image, we then feed it onward to the discriminator. Previously, we gave the discriminator a real image, and the discriminator tried to output a value near 1. Now the discriminator tries to output a value near 0. However, we also train the generator to try to fool the discriminator, to try to make the discriminator output a value near 1. It turns out that you can analyze this through the language of game theory, and we can think of there being a Nash equilibrium that indicates exactly the situation where the generator has recovered the training distribution perfectly. At the Nash equilibrium, the best that the discriminator can do is guess randomly, and the generator is able to perfectly reproduce the training data. Over the past few years, there's been rapid progress in the development of generative adversarial networks for creating faces. In the original paper on generative adversarial networks, my co-authors and I were able to train models that could generate low-resolution grayscale images of faces. But afterward, faster GPUs and better generative adversarial network algorithms have resulted in higher and higher quality faces, to the point that modern generative adversarial networks are able to generate photorealistic images at resolutions of 1024 by 1024, as shown on the right end of this slide. But faces are actually relatively easy. Every photo is of a face that has been centered, and it's usually a face that's more or less aimed toward the camera. And there's really only one kind of object in each of these photos. It turned out that it was a lot harder to get generative models to create a wide diversity of different kinds of objects. We've also seen rapid progress create all 1,000 different objects in the ImageNet dataset until about 2016, with the introduction of Augustus Odina's class-conditional auxiliary class GAN. The basic idea behind this model is that the generator is told to generate a specific image from a specific class. After this basic framework began to work successfully, it has rapidly improved. Takeru Miyato at Preferred Networks created a model that could generate much more realistic images by using a special normalization approach to make the learning process smoother. And this year, my team at Google, on a project done primarily by intern Han Zhang, created a model that uses attention to create highly realistic images on the ImageNet dataset.